In this video, we are solving exponential equations. I want to start by introducing the one-to-one property. It states if b to the x is equal to b to the y, then x is equal to y. This property is always our plan A. It's easy to use. So as we're looking at our general strategy for solving exponential equations, if both sides can be raised as exponentials with the same base, do so and then apply our one-to-one property. Always plan A, much easier approach. But we know that that's not always going to work, so plan B is to rewrite the equation in logarithmic form to get the variable out of the exponent and then solve the resulting equation. And we'll be using our property that says log base b of x equals y is rewritten b to the y equals x for our plan B there. Okay. So let's solve. We'll find the exact answer and estimate answer to the nearest thousandth. So like I said, I always try to do the one-to-one property, try to rewrite each side as the same number to a power. So I look at 1/3 and 27, and they're both related to 3. We know that 27 is 3 to the third, and then 1/3, that is 3 to the negative first. And that's still raised to the y power. When you have a power raised to a power, we multiply our exponents together. This becomes 3 to the negative y equals 3 to the third. Now that we have each side written with a base of 3, we can set the exponents equal to each other by our one-to-one property. Negative y equals 3, therefore y is equal to negative 3. Our next example, we want to solve e to the 2x minus 4e to the x minus 5 equals 0. This equation we recognize to be quadratic in form. We know something's quadratic in form when written in descending order. The second exponent is half the first, and the third term is a constant. You could factor by substitution if you wanted to, letting u be equal to e to the x, but I'm just going to factor it. We're going to get e to the x's in first position. Hopefully we're comfortable with this by now, but again, if you want to use substitution, please do that. Two numbers that multiply together to give us negative 5, add together to give us negative 4. Negative 5 and positive 1 work. Next, we'll apply our zero product property and set each of these factors equal to 0 and solve those resulting equations. Looking at e to the x minus 5 equals 0. We'll start by isolating the exponential. So e to the x is equal to 5. The one-to-one property won't work here, so we're going to go to our plan B and rewrite it in exponential form. This becomes the natural log of 5 is equal to x. There is our exact answer. The directions also ask for an estimate to the nearest thousandth, so just pop that in your calculator. Natural log can be done in the calculator. We get x equals 1.609. Now let's solve our second equation. Again, we will isolate the exponential portion. E to the x equals negative 1. The one-to-one property does not apply, so we'll rewrite it in logarithmic form. Natural log of negative 1 is equal to x. Notice that we have a negative inside the argument of our log. This cannot happen. Has to be a positive. So this gets thrown out as an extraneous solution, and we just have the one solution of natural log of 5. Our next example is about as typical as it can get. This would be an excellent exam question. 9 to the x minus 4 equals 5 to the 3x plus 1. I always try one-to-one property first, but that's not going to apply here. That means we're going to have to rewrite it in logarithmic form. We can choose between rewriting it base 9 or base e. When there's a different number of terms in the exponent, I recommend choosing the base that has more terms in the exponent as your logarithmic base, but in this example there's a tie, so it really doesn't matter which one we choose. I'm going to choose 5. So this becomes a log base 5 of 9 to the x minus 4 equals 3x plus 1. One of the x's is now out of the exponent, but the other is not. So we're going to use our property of logs and turn our exponent into a coefficient. Now, since that exponent that you're turning into a coefficient is more than one term, you got to make sure that you put that in parentheses, because we're ultimately going to have to distribute our log base 5 of 9 to that. So let's distribute our log base 5 of 9. We're kind of distributing backwards. This gives us x times log base 5 of 9 minus 4 times log base 5 of 9 equals 3x plus 1. Great, all of the x's are out of parentheses, they're out of exponents, they're where we can solve for them. But notice that our x shows up more than one time. Anytime a linear variable shows up more than once, and that's the one we're solving for, we do the same technique of getting all the terms containing that variable on one side of the equation, all the terms that don't contain that variable on the other side of the equation, and then factor the variable out. So let's do that. Let's move our 3x over to the left side and our 4 log base 5 of 9 over to the right side. Great. Now we see that we have a common factor of x on the left-hand side, so we will factor that x out. When we factor it out, we're left with log base 5 of 9 minus 3 equal to 4 log base 5 of 9 plus 1. And then the last thing we'll have to do here is divide both sides by what we have in the parentheses. We get x to be equal to 4 times log base 5 of 9 plus 1 over log base 5 of 9 minus 3. And that is our exact answer. If we want a decimal approximation, which again the directions ask us for, we're going to have to use change of base formula here since our calculator does not do log base 5. This will become 4 times the natural log of 9 over natural log of 5 plus 1 in the numerator, and then natural log of 9 over natural log of 5 minus 3 in our denominator. And remember, with change of base formula, you can either use natural log or common log. I just prefer to use natural log. And when we type this into our calculator, we're going to get negative 3.952. Right. Let's try another one. X squared times 6 to the x equals 6 to the x. So this is definitely a step up from some of the others that we've seen before. So let's just think about what we see. We're solving for x. X is located both in the exponent and outside of the exponent, so we're kind of going to have to deal with both of those things. I notice that 6 to the x shows up on both sides of my equation, so that makes me think, well, if I put both of these terms on the same side of the equation, I now have a common factor of 6 to the x. Factoring out 6 to the x, I'm left with x squared minus 1. So you'll notice that in this factoring process, I've separated the x in the exponent with the x not in the exponent. So now I'm going to apply zero product property. 6 to the x is equal to 0. X squared minus 1 is equal to 0. And I can solve each of these equations. 6 to the x equals 0. One-to-one property is not going to work, so I'm going to rewrite it in logarithmic form. This is going to be log base 6 of 0 equals x. Notice that our argument is a number that is not positive. The argument always has to be positive in a log, so this is an extraneous solution that gets thrown out. Turning our attention to solving x squared minus 1 equals 0, I'm going to use square root property. X squared is equal to 1, so x must be equal to plus or minus 1.